Assalamu alaikum students. Myself Dr. Anam Hanif from Y Engineering College, Department of Electrical Engineering. Today I will deliver a lecture on operational amplifier, which is one of the most fundamental and widely applicable topic in network theory. So in this lecture, we will go through the operational amplifier circuits using the network analysis techniques that you have already covered in previous lectures. So we will start with an introduction to operational amplifier, then explore the different input modes of operation and also go through the several key configurations including inverting, non-inverting, summing and difference amplifiers using KCL and KVL methods. Okay, so let's start our lecture of operational amplifier with a clear introduction to what they are and why they matter. So here is the core definition of an operational amplifier. That an operational amplifier is an active circuit element designed to perform mathematical operations. So you all students are familiar with active circuit elements and passive circuit elements, right? Active elements are those that can add energy to a circuit, okay? And the passive elements like resistors, capacitors, and inductors are those which cannot deliver more energy than they receive, okay? Although operational amplifier require an external power supply, but they can amplify signal. What that means? The output signal can have more power than the input signal. So this make operational amplifier in a active circuit element, and they can be used to build amplifiers, oscillators, filters, and other signal processing circuits. Okay, so where we actually use operational amplifier for amplitude and polarity control, to build oscillators, for filter circuits to block specific range of frequencies, and for instrumentation circuits like in medical devices, test equipments, and also in sensors we can use operational amplifier. So here is the key point about operational amplifier, that is our linear and linear integrated circuit. What does linear mean? Linear means their output is directly proportional to their input, that there is no sudden jumps or no digital steps. Okay, and what does integrated circuit means? It is not just one transistor or resistor, it is complete system on a single chip. So the let's peek inside to the constructions of operational amplifier, that includes number of transistors, diodes, resistors, and capacitors. What does transistors purpose in operational amplifier? Transistors are used for amplification, and diodes for protection in biasing, and resistors for setting gain, and capacitors for filtering or for stability purposes. Okay, all these components are fabricated on a single piece of silicon. It is packaged in a single case to form a functional circuit. So here is the typical operational amplifier representation, जो कि आपने लैब एक्सपेरिमेंट करते हुए भी देखा होगा, जिसकी 8 पिन्स होती हैं, टोटल 8 पिन्स होती हैं इसकी, ठीक है. दिस इज बेसिकली 741 IC. Here pin number 8 is unused and 1 and 5 pins are used for advanced features like offset null adjustment. Okay, तो commonly pins यूज होती हैं जो भी लैब एक्सपेरिमेंट करते हैं सर्किट एनालिसिस के लिए, वो होती हैं 2, 3, 4, 7 and 6. Pin number 2 is for inverting input, pin number 3 is for non-inverting input, pin number 6 is for output, and pin number 7 is for positive terminal of power supply. And pin number 4 is negative power supply. Okay, often connected to negative terminal of the battery or ground in a single splice setup. Okay, तो यहाँ पे मैं एक पॉइंट दोबारा रिपीट कर लूँ। ऑपरेशनल एम्पलीफायर को वर्क करने के लिए एक्सटर्नल पावर की ज़रूरत होती है, जो कि जिसका पॉजिटिव टर्मिनल हम 7 नंबर पिन के साथ कनेक्ट करते हैं और नेगेटिव टर्मिनल 4 नंबर पिन के साथ कनेक्ट करते हैं। ठीक है, विदाउट एक्सटर्नल पावर दिस इज ओनली ए पीस ऑफ सिलिकॉन। Okay, so in circuit diagrams for analysis purposes, we only draw this symbol instead of drawing a whole 8-pin chip. We only draw this universal symbol in triangular form. Okay, which has 2 input in left side and 1 output in right side. Here negative input represent the inverting input and the positive plus input represent the non-inverting input. So there is a rule. If you apply signal to non-inverting input, the plus side, the output will have the same polarity. Positive, it means, what does it mean? Positive input give positive output. Okay, if you apply a signal to the inverting input, the minus side, the output will be inverted and the positive input gives नेगेटिव आउटपुट। ओके, आप इसको कह सकते हैं नॉन इन्वर्टिंग इनपुट इज फॉलोअर, इट फॉलोज व्हाट यू गिव इट। ओके, एंड द इन्वर्टिंग इनपुट इज फ्लिपर, इट flips the signal upside down. Okay, so this simple behavior is the foundation of every operational amplifier circuit that we will study in the slides. Now we will go through the types of different ways we can feed signal into an operational amplifier, that is known as input mode operation. Okay, so there are 3 main types we will look at: single-ended input, double-ended input, and common mode. The first one is the single-ended input. This means the input signal is connected to one operational amplifier input and the other input is connected to ground. Okay, if the signal goes to the positive input, the output will have the same polarity as the input, and if it goes to the negative terminal and the positive terminal is grounded, then the output will be opposite to the input signal. So in single-ended mode, the operational amplifier act either as a follower, inverter, depending on which input you use. Okay, and the second one is the double-ended or differential input. Okay, here we apply signals to the both inputs. If same signal is applied to the both input, the output is amplified and in phase with the difference between them. Okay, if separate signal, different signals are applied to the both inputs, that is Vi1 and Vi2, then the operational amplifier amplifies the difference, that is Vd, between them. Okay, so this mode is basically useful when we want to compare two signal or reject common noise. Okay, the third one is the common mode operation. कॉमन मोड ऑपरेशन में दिस इज स्पेशल केस जिसमें एग्जैक्ट सेम सिग्नल को दोनों इनपुट्स पे अप्लाई करते हैं. व्हेन आइडेंटिकल सिग्नल इंटर बोथ इनपुट, operational amplifier sees no difference between them, so the result is 0 volt at the output because the two signals are amplified equally but with opposite polarities. Okay, so they cancel out each other. So this is why these operational amplifiers are good at rejecting unwanted common noise that appears on both input lines. Okay, so to summarize, single-ended uses one input, double-ended uses both inputs with different signals, and common mode uses both inputs with the same signal. Okay, so understanding these mode operation is essential before we move into the basic operational amplifier working principle and circuit analysis. So now we move to the basic operation of the operational amplifier. Understanding how amplifier work is essential for analyzing any operational amplifier circuit. So we will split it into two sections. Is non-ideal operation and ideal operation. Non-ideal operation reflect the real physical amplifier with real world limits, and ideal operation is a simplified model we can use for more circuit analysis. Okay, so the ideal operation will be used throughout the analysis. सर्किट एनालिसिस के लिए हम आइडियल ऑपरेशन ही यूज करते हैं जो कि सिंपल मोर सिंपल देन दैट इज मोर सिंपल देन नॉन आइडियल ऑपरेशन. Now let's start with an ideal operation where a real operational amplifier has three characteristics. The first one is the high open loop gain, that is about 1 million. Okay, the open loop gain here, the equivalent circuit of non-ideal operational amplifier is shown, where open loop gain is denoted as A in the voltage gain of operational amplifier when there is no feedback connected. Okay, in real operational amplifier this gain is very high, typically around 1 million. Okay, 10 raised to power 6. So this means that for just 1 millivolt of difference between these two voltages, these two inputs, the operational amplifier would try to produce 1000 volts at the output terminal, which is obviously limited by the power supply. So huge gain is what allows the amplifier to be used in closed loop configuration with feedback, where we can precisely control the gain using external resistance. Okay, the second characteristic is high input resistance, Ri, that is approximately equal to 2 mega ohm. So this means the operational amplifier uh, that is represented as Ri in this equivalent circuit. So this means the operational amplifier draw very little current from the input source, and in network term it behave almost like an open circuit at the input. Okay, so which is why in the ideal model we assume infinite input resistance. R input is approximately equal to infinity for ideal case. Okay, and the third characteristic is the low output resistance, that is equal to 75 ohm, that R naught is equal to 75 ohm. Low output resistance means operational amplifier can deliver current to a load without the output voltage dropping significantly. So in the ideal model, we simply this to zero output resistance are not approached to this value is 0, meaning the output act like a perfect voltage source. Okay, so here The difference between these input voltages are given as VD. Here V1 is the voltage in the inverting terminal and V2 is the non-inverting terminal. So this difference is what gets amplified by the very large open loop gain A to produce the output voltage that is equal to AVD. Okay, so even a small difference between V1 and V2 results in large output voltage. Okay, so now for our analysis purposes, we simply consider the ideal case. Okay, for circuit analysis, we consider the ideal operation. The ideal operational amplifier has three characteristics. The first one is the infinite open loop gain. That is, gain is approximately equal to infinite. And the second one is infinite input resistance. That is, input resistance is infinite. And the third one is zero output resistance, and R naught is approximately equal to 0. So here is the ideal operational amplifier model. We notice that there is no current flows into the input pin. I1 equal to 0 and I2 is also equal to 0. This is because the input resistance is infinite. What does this mean practically? It means that any small voltage difference between the would produce an infinite output voltage, which is physically impossible. Okay, but because we always use operational amplifier with negative feedback, so this assumption lead to very useful rule, that also because the gain is infinite, the differential voltage is 0. Here Vd will be equal to 0, and this leads to the important result, that is V2 equal to V1. So that means the two input terminals are at the same voltage, which is called the virtual short. Okay. So now let's restate the rules of the ideal operational amplifier. Okay, that is I1 equal to 0 and I2 equal to 0. This is the ideal operational amplifier model, where these assumptions, that is I1 equal to 0 and I2 equal to 0, lead to two rules, that there is no input current and inputs are at the same voltages. Okay, there is two rules, that there is no input current, that is I1 equal to 0 and I2 equal to 0, and the inputs are at the same voltages, that's V2 equal to V1. So using these rules, we can analyze inverting amplifiers, non-inverting amplifiers, summer and difference amplifier. Different type of configuration, we can analyze these different type of configurations using these two assumptions, that is the first one and second assumptions. Okay, so now we will apply the ideal operational amplifier rules to our first circuit, the inverting configuration. Okay, here this figure show the equivalent circuit of an inverting amplifier In this circuit, the non-inverting input is grounded and the input signal, that is Vi, that is input signal, is connected to the inverting input through resistor R1. Okay, and the feedback resistor RF is connected between the inverting input V1 and the output V0. Okay. So this setup is called this all setup is called negative feedback because the output is fed back to the inverting input. Okay, basically this is the closed loop configuration with negative feedback. Here's what happens basically. If Vi input voltage is positive, current flows through R1, that is I1, toward the virtual ground at V1. Okay, so the operational amplifier responds by driving V0 negative to pull current back through RF and keep V1 at 0. Okay, so a negative output proportional to the positive input, and conversely a negative input produces a positive output. Okay, so our main goal is to find a relationship between the input voltage and output voltage. So in previous circuit we apply KCL at node 1. Okay, so here is the node 1, we apply KCL. According to KCL, I1 equal to I2. Here I1 is V1 minus Vi. Okay, here by applying nodal analysis, I1 will be equal to Vi minus V1 over R1, and I2 will be equal to V1 minus V output over RF. Okay, so by applying KCL at node 1, we'll get this equation. Now recall the ideal operational amplifier rule, that is V1 equal to V2. Okay, so here V2 is grounded and V1 is also virtually grounded. So these two voltages are equal to 0. Since the non-inverting pin is grounded, so inverting voltage is also virtually grounded. So we will get Vi over R1 is equal to minus V0 over RF. So from here V output will be equal to minus RF over R1 into Vi. Okay, so from the previous result we can directly write the voltage gain AV, that is the ratio of output voltage over input voltage, and the negative sign here in gain is very important. It means the output signal is inverted compared to the input. This negative sign represents that the amplifier is inverting. Okay, so for inverting amplifier, the gain is set by the ratio of feedback over our input resistor, that is R1, and the output is inverted related to the input, this negative sign represent. Okay, so next next configuration is a non-inverting amplifier. Okay, here figure 5.16 is the equivalent circuit of non-inverting amplifier, where the input voltage V input Vi is directly to the non-inverting input, that is the plus sign, and resistor R1 is connected between ground and the inverting input. Okay, the feedback resistor is connected between the output and the inverting input. Here I1 and I2 are represented by red arrow. So we can again, to find the voltage gain, we apply KCL at the inverting pin. So that is equal to I1 equal to I2. Okay, so I1 will be equal to 0 minus V1 and I2 equal to V output minus V1 minus V output, our RF. Okay, so by rearranging this equation we can find out the V output, our V input. Okay, the from that result voltage gain is found by taking the ratio of output voltage over input voltage, that is equal to 1 plus RF over R1. Notice that there is no negative sign in the, so this means the output has the same polarity as the input, so that is why this is called non-inverting amplifier. Okay, so this is the voltage follower or buffer. This is the special case of the non-inverting amplifier. Okay, that is known as the voltage follower or buffer. If this, if we set let RF equal to 0 and R1 equal to infinity. Okay, in circuit amplifier, in previous circuit, non-inverting circuit. Okay, here if we consider that RF equal to 0 and R1 equal to infinity, then in this configuration the, so we will get this, and in this configuration the output is directly connected to the inverting input. Okay, the output is connected to the directly to the inverting input here, and the input goes straight to the non-inverting input. Okay, that input voltage is going straight to the non-inverting input, so the result is V output is equal to V input. ओके, आउटपुट वोल्टेज इक्वल होगी इनपुट वोल्टेज के, तो गेन हमारे पास किसके इक्वल होगा, गेन यहाँ पे अकॉर्डिंग टू दिस फार्मूला equal to 1. Okay, so this circuit does not amplify voltage, but it is very useful for isolating stages in circuit because it has high input impedance and low output impedance. Okay, so this is known as a buffer amplifier or voltage follower. So now let's move to another useful operational amplifier configuration, that is the summing amplifier. Okay, also called summer. So figure 5.21 is the representation of the summing amplifier equivalent circuit. It looks similar to the inverting amplifier, but now we have multiple input resistors. In this case, three resistors R1, R2 and R3 are added. Okay, Also, a summing amplifier combines several input voltages and produces an output that is sum of these inputs. Okay, so to it is an inverting amplifier with multiple inputs. So we can have more than three inputs, just add more resistors. Okay, we apply KCL at node A, that will give I is equal to I1. We will apply KCL at this node. Okay, that will give I is equal to I1 plus I2 plus I3. Okay, and I1 will be equal to V1 minus VA over R1. I2 is equal to V2 minus VA over R2, and I3 is equal to V3 minus VA over R, V3 minus VA over R3, and I is equal to VA minus V naught over RF. Okay, so note that VA equal to 0 by applying, so this is the ideal operational amplifier rule. Okay, VA equal to 0 and VB is also equal to 0 because non-inverting input is grounded. Okay, so VA equal to 0. So substitute the VA, we will consider VA equal to 0 in all these equations. Then I1 will be equal to V1 over R1, I2 equal to V2 over R2, and I3 is equal to V3 over R3, and I is equal to VA over RF. Sorry, VA equal to 0, I is equal to minus V output over RF. So putting it all together in this equation, we will get V output is equal to minus RF over R1. We will get this expression. Okay. Now another configuration, we move to the difference amplifier, a circuit that amplifies the difference between two input signals. Okay, so this is especially useful in application where we need to compare two voltages, that is V1 and V2, such as in sensors or other instrumentations. We require to compare the two voltages. So where we use this difference amplifier configuration. Okay, so figure 5.24 show the difference amplifier equivalent circuit. It has two input signal V1 and V2 applied through resistor R1 and R3. Okay, the goal is to produce an output operational to V2 minus V1. Okay, so to find this, we have two nodes here, we A and B node. Okay, this is the these are two nodes, so we will apply KCL. Okay, we will apply KCL to, we will analyze this circuit by applying KCL at node A and node B. At node A, the current through R1 and R2 are equals. So current through R1 is V1 minus VA over R1, and current through R2 is, here we are considering this circuit. Okay, current through R2 is VA minus V naught over R2. Okay, so by rearranging this equation, we will get the expression for V output. Then will apply KCL at node B. That gives, we will apply KCL at node B. That will give that current through R3 and R4 is equal. Okay, so current through R3 is V2 minus VB over R3, and current through R4 is VB minus 0 over R4. Okay, so by rearranging this equation, we will get the expression for VB. Okay, so by applying the, we recall the ideal operational amplifier rule, that is VA is equal to VB. So the voltage at the inverting and non-inverting inputs are equal. So substituting VA with the expression for VB into the previous equation from node A, we will get V output is equal to this one. So by simplifying this we will get V output is equal to R2 over R1 into this term into V2 minus R2 over R1 into V1. Okay, so if we choose R2 over R1 equal to R3 over R4, and we consider this equal to one constant, that is K, which represent the gain. So we see that V output will be equal to K into V2 minus V1. Okay, so this show the output is simply the difference between two voltages V2 and V1 multiplied by again K. So this difference amplifier is widely used in noise cancellation and also sensor signal conditioning, where we find the two difference between two voltages. Okay, now I will conclude my lecture by going through the overview of operational amplifier applications in terms of control sources. Okay, there are four main types of control sources. The first one is the voltage controlled voltage source. Here the output voltage is controlled by the input voltage. Okay, and the non-inverting and inverting amplifier we have studied earlier are example of VCVS, where the output voltage depend directly on the input voltage. Okay, and the second type is the voltage controlled current source. In this type, the output current is controlled by an input voltage. So this is useful in applications like elevators or other loads where you want the current to be precisely set by voltage signal. Okay, and the third one is the voltage source. Here the output voltage is controlled by an input current. And the fourth one is the current controlled current source. In this case, the output current is controlled by an input current, and this can be used in current amplification or mirroring circuits. Okay, so now that's all for today's lecture, and in the next lecture we will cover the numerical problems related to operational amplifier. And thank you for attending the lecture. Allah Hafiz.